Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the lecture 2 of module 12. In the lecture 2, we are going to cover the topics such as the spreading centers, evolution of the oceanic lithosphere, in which we are going to discuss about two models of the evolution of the oceanic lithosphere, that is half space model and the plate model, and then we will have the summary of today's lecture. Before we delve into the lecture today, let's have a recap of what we have learned in the previous lecture. We learned that the plate tectonics treats the Earth's outer shell as made up of about 15 rigid plates. Those are around 100 km thick and they move relative to each other at speeds of few centimeter per year. We also observed that the spreading centers, subduction zones, and transform fault as three types of plate boundaries, which means there are three types of plate boundaries possible. Those are basically the convergent plate boundary, that is at the subduction zone, and there are the divergent plate boundaries, that are spreading centers or the rift zones, and there are transform faults where the plates move relative to each other horizontally. And then we learned that the volcanism, hydrothermal circulation through cooling oceanic lithosphere, and the cycle of uplift and erosion are processes by which the solid earth interacts with the ocean and the atmosphere. The interplate earthquakes both delineate plate boundaries and show the occurring occurrence there, which means if you will plot all the epicenters that are happening all across the globe, they will basically delineate the plate boundaries, and we have seen that in the previous lecture. Then we learnt about the Euler's theorem, that it states that the displacement of any rigid body, which is a plate in this case, with one point relative to the center of the earth fixed, is a rotation about an axis. Hot spots and deep mantle plumes are used to track the absolute plate motion. The relative and absolute Euler's vectors are simply related at omega sub ij is equal to omega I minus omega j. Now let's start with the lecture today. First we will learn about the geometry of the ridges and the transform plate boundaries. So lithosphere, as we know, forms at the spreading centers. They are also known as rift zone, where the hot magma gets bulge up and then come out onto the surface and then spread on both sides of the mid-oceanic ridges. As it spreads out, then it forms the new lithosphere, and this new lithosphere getting compensated at the other boundary, that is at the subduction zone. So lithosphere forms at spreading centers and they provide key evidence for the thermal mechanical processes that control the formation and evolution of the oceanic lithosphere. So you can see that there the plates are moving away from each other. So this is a divergent plate boundary with a spreading center, you can say. And you can see the movement of the lithosphere in this direction. Here also it is moving in this direction, and here somewhere at the subduction zone it may be subducting beneath another plate and then being compensated at that particular subduction zone plate boundary. So here at the rift zone you can see the magma is bulging up and then forming a new lithosphere around it, and with age this new lithosphere will move away at a rate of the movement of the plate that is sliding over the asthenosphere, that is here the asthenosphere, which is a rock melt as pressure is released. So basically this rock will melt in the form of magma and then it will move up and will move out onto the surface and then form a new lithosphere here. Now let's talk about the spreading center a little bit. So here in this picture you can see this is the portion of spreading ridge offset by the transform fault. So you can see there is the ridge here, and here the plates are moving in this direction, and those are being represented by this beach ball diagrams. Those are basically the normal faulting. And here, since it is a transform plate boundary, so you can see this is represented by a strike slip fault. And if you look at the arrow of the other side plate that is moving in left direction, so it is basically a left lateral strike slip fault or the left lateral transform plate boundary, and it is being represented by this beach ball diagram. And you can see there is another transfer plate boundary here. Here you can see the movement of the other plate is in the right direction, so it is a right lateral strike slip fault, or you can say the right lateral strike slip transform plate boundary. And as you move away in opposite direction along the plate like this, so the transform faults basically is basically having a segment of the plate boundaries here, and that is in between the plates that are moving relative to each other. And you can see at a faraway zone from the rifting zone, the seismicity will be around minimal, or you can say the no seismicity will be observed. So this is what it is written here. The figure shows a portion of a spreading ridge offset by transform fault. Because new lithosphere forms at ridges and then moves away, transform faults are segment of boundaries between plates across which lithosphere moves in opposite direction. Transform faults can have either right or left lateral strike slip fault motion. That is what we have discussed over here and here. So here it is a left lateral strike slip faulting, and here at this particular region the transform fault is of right lateral strike slip fault. Now you can see this is the cross section of the mid-Atlantic ridge, and at these locations you can see the earthquake hypocenters are being marked here, and which basically are consistent with the normal faulting along the east side of the valley. So this basically confirms that it is basically the ridge, and at this particular zone the motion is of normal faulting type. So at the mid-oceanic ridges or the mid-Atlantic ridge, the faulting type is normal faulting. Then we are going to discuss about a powerful model, that is a half-space model. Now we are going to discuss about for the oceanic lithosphere, or you can say for the evolution of the oceanic lithosphere. So a powerful model is presented for the formation of the lithosphere by hot material at the ridge which cools as the plate moves away. So here you can see in this diagram, this is a model for the cooling of the oceanic plate. So you can see at the ridge we are considering x is equal to 0. As you move away, the x will keep on increasing in this direction or in this direction at the surface. And as soon as the magma is coming out from the asthenosphere onto the surface at x is equal to 0 location, that is the location of the ridge, then it spreads out onto the surface, and as you move away, then this lithosphere is basically getting thicker and thicker at this particular location. So you can see in the half space the asthenosphere is having the temperature Tm, and at the surface, or you can say at the sea floor here, the temperature is T in subscript S, and here you have the lithosphere. And if you look at this particular diagram here, the lithosphere is moving at a velocity v, and we are basically seeing this lithosphere in a vertical section, and these vertical sections are basically divided into three parts. You can see at basically t is equal to 0 it has this position, as it moves away it has t is equal to t1, and at t is equal to t2 it has this position. And q is representing the heat flow, rate of heat flow, and the time that the lithosphere is taking to move at a distance x with velocity v, the time is x by v. In this model, material at the ridge at a mantle temperature Tm, that is approximately in between 1300 to 1400 degrees centigrade, is brought to the ocean floor, which has temperature T in subscript S. The material then moves away at a velocity v while its upper surface remains at T sub s. The assumption that we are going to make here, since the plate is moving faster than the heat is conducting horizontally, so in that case we are going to consider a assumption. We are considering that the heat conduction is happening in the vertical columns only, because the plate is moving faster than the heat is conducted horizontally. So this is the assumption here: the plate slides away from the ridge faster than heat is conducted horizontally, and we can consider only vertical heat conduction. It is similar to the cooling of a half space originally at temperature Tm. So you can see we have also indicated here the asthenosphere, that is a half space, is at temperature T sub m, whose surface is suddenly cooled to temperature Ts at T is equal to 0. So at T is equal to 0, you can see here at T is equal to 0. So at the surface you can see the temperature is T is equal to Ts, that is in contact with the ocean. So we may apply the one-dimensional heat flow equation here, and then the one-dimensional heat flow equation has some parameter that, like the thermal diffusivity parameter, there is this specific heat parameter. The equation will involve, this is a one-dimensional heat flow equation that says that the delta T by delta T as a function of z comma T is equal to K by rho Cp delta square T z comma T by delta Z square is equal to K delta square T by delta Z square z comma T. So K is the thermal diffusivity, is a property of the material that measure the rate at which the heat is conducted, and this kappa is equal to K by rho Cp, where K is the thermal conductivity. So this particular parameter is kappa. We should not call it K, it is kappa. So kappa known as the thermal diffusivity, and kappa is further equal to K by rho Cp, where K is the thermal conductivity and rho is the density, and Cp is the specific heat at constant pressure. That is why in subscript you have P. So this is C, specific heat at constant pressure. And if you want to have the solution for this particular differential equation of one-dimensional heat flow, then the solution of this equation may be represented by this particular expression here. This T as a function of Z or Z or depth comma time T is equal to Ts, this is the temperature at the surface, in bracket temperature of the half space, that is the asthenosphere, minus temperature of the surface, and then this function is there, that is basically the error function. In argument you have z by 2 under root kappa t, where this particular function, error function, as a function of s can be represented as 2 under root pi integral 0 to s e minus sigma square d sigma, and its behavior looks something like this. So you can see as s moves from 0 to 3, the value of error function reaches to 1. And if you look at this particular diagram here, on the y-axis the depth is increasing downward, and here at t is equal to 0, and then you have the temperature that is increasing to the temperature of half space, and you can see that the cooling actually begins at the surface and then it deepens with time. So you can see the curves are moving like this. At t is equal to 0 it has almost flat, and then t is equal to 1 it has this particular pattern, and then t is equal to 5 it has this particular pattern, t is equal to 10 it has this pattern. Let's suppose the sea floor temperature is Ts is equal to 0 degree centigrade. So surface temperature we are assuming 0 degree centigrade. Then T z comma T is equal to Tm error function z by 2 under root kt, that provides the temperature at depth z for material of Ht. So you can see the temperature at a particular z depth for a material of Ht can be represented as Tm, that is the temperature of the half space, and then error function which is z by 2 under root kt or kappa t. The age of the lithosphere is T is equal to x by V. So where x is the distance and the v is the spreading rate. So t as a function of distance and depth can be represented as Tm error function z by under root 2 under root kappa x by v. So now let's define an isotherm, which is basically the lines of constant temperature, and where this particular argument is remains constant. So what we are going to do, this argument we are keeping it as equal to c, and then the new depth will be defined as z in subscript c. So z in subscript c divided by 2 under root kappa t is equal to c, or z in subscript c is equal to 2c under root kappa t. The depth to a given temperature increases as the square root of the lithospheric age. So this is what it is written. The depth to a given temperature is basically increases as the square root of the lithospheric age. So here is the under root of t is there. So that is why it is there. So this means that the lithosphere cools with time and isotherms deepens with the square root of the age. So this is the isotherm here. So you can see this basically deepens with age. So it will go something like this. And then it further indicates that the ocean depth should vary with age. It is dependent upon the time here. So it is basically dependent upon the depth is dependent upon the age of the lithosphere. So now this is the parabolic increase in ocean depth and plate thickness in the half space cooling model. So the increase in ocean depth with lithospheric age due to the cooling of the lithosphere can be modeled using isostasy, the assumption that the mass in a vertical column is same for all ages. So as per the principle of isostasy, the mass in this particular column and this particular will be equal, and that will be used for further calculation here. So at z is equal to 0 and up to z is equal to h comma h as a function of t time, we are considering that is the depth of the water level of the ocean, and then beneath it we have from ht to mt we have the plate thickness, and underneath we have the asthenosphere. Assume that the lithosphere defined by T is equal to Tm isotherm has thickness 0 at the ridge and Z is equal to Mt as Ht, where the water depth is Ht. So this is what it is here. So this particular lithosphere, and it is having the depth here 0, and as you move away with age the thickness will keep on increasing, and that will reach to Z is equal to Mt, and on top of it you have the ocean depth as, or the water depth as, Z is equal to h as a function of time. Let's assume that the asthenosphere is at constant temperature Tm and has density rho m. The temperature and thus density in the cooling lithosphere vary such that at point z, t the temperature is T z, t, and the corresponding density is, the density can be defined as rho as a function of depth, time is equal to rho m, plus this is the density of the asthenosphere here as a gradient plus a gradient with respect to temperature of density in bracket Tz, t minus Tm, and this particular term can be replaced with rho dash as a function of z, t. The change in density due to temperature at constant pressure is given by coefficient of thermal expansion. So the density gradient with respect to temperature is related by a coefficient of thermal expansion, that is alpha, that is 1 by v by del t at constant pressure, that is equal to minus 1 by rho in bracket del rho by del t at constant pressure. So this particular term here will be used to replace this particular value here. So the rho dash that we have seen, this rho dash z comma t. So rho dash z comma t is basically what? It is del rho by del t in bracket t z comma t minus tm, and then we are going to replace this thing with this particular coefficient here. So this will become alpha rho m tm minus t z comma t, or you can write this particular value of Tm here. So you can see that it will become from this equation here, T by Tm is equal to error function Z by 2 under root Kt kappa T. So when you will replace it with this, then it will become something like this. So if the density of the water is rho W, then the equal mass, what we are saying from the principle of isostasy, that the mass in both of the column should be same. So when this mass will be same, that means rho m, that is the density of asthenosphere at the location of ridge, here you can see. So this rho m, and the total height is mt. So that total height we are considering mt here. So rho m into mt will be equal to rho wst. This is the mass of the water in this particular column here, plus mass of the plate in this particular column. So ht to mt, rho m plus rho dash z comma t dg, so which gives the isostatic condition for the ocean depth, something like this: ht is equal to 1 by rho m minus rho w integral ht to mt rho dash z comma t dz. Because temperature and density in the plate are defined for all values of Z, the thickness of the plate is defined as some chosen isotherms. Let's Z is equal to Z dash is equal to Z minus Ht, and Mt is tending to G infinity. Then we can rewrite this particular equation in the form something like this: Ht is equal to alpha rho m Tm by rho m minus rho w integral 0 to infinity 1 minus error function z dash by 2 under root kt dz dash. To evaluate the integral, we can substitute this integral, the value, the z dash by 2 under root k kappa t as s, and then we can integrate it by part, and then what we will find that 0 to infinity 1 minus error function of this ds is equal to 1 by under root pi. So this entire value will be replaced by 1 by under root pi. So the ocean depth, we can find the ocean depth here. This ocean depth is equal to 2 under root kt kappa t by pi alpha rho m tm by rho m minus rho w. So you can see the ocean depth can be found out using this formula. So ocean depth is basically increasing as square root of the plate age. So here you can see the square root of the plate age here. The cooling of the lithosphere should also cause heat flow at sea floor to vary with age. By Fourier's law of heat conduction, the heat flow, that is represented by Q, at the sea floor is the product of the temperature gradient at the sea floor and the thermal conductivity K. So K multiplied by temperature gradient, the product is called the heat flow at Z is equal to 0. And then approximating the gradient at the surface by the average gradient through the lithosphere. So Q as a function of T is equal to K delta T by delta Z. This is the average gradient, and that will be approximately equal to K T subscript M, that is the temperature of the asthenosphere, and then divided by under root kappa T. T is the age. That is basically predict the heat flow decreases as the square root of the age. So heat flow basically decreases as the square root of the age, while the ocean depth increases as the square root of the plate age. The same result can be obtained by differentiation of the temperature structure using this particular formula. So you can see d by dz error function s, that will be equal to 2 under root pi e to the power minus s square ds by dz, and this will finally give you the heat flow as k tm by under root pi kappa t. So this model, this is the half space model. So this model which predict that the lithospheric thickness, heat flow and ocean depth vary as square root of age for all ages is called the half space model. So you can see we have represented the heat flow and also the thickness of the lithosphere and the ocean depth as a square root of the age of the lithosphere. So that is why it is known as half space model. And in this model, the lithosphere is the upper layer of a half space, and that continues cooling for all time. In reality, the oceanic lithosphere never gets older than 200 million year old because it gets subducted at the other end. And this model basically does a very good job of describing the average variations of ocean depth and heat flow with lithospheric age. So you can see with time, with depth, the temperature is increasing downward, and this is the half space model, and it describes the variations in the ocean depth as a square root of the temperature, a square root of the time, and also for the heat flow, and also for the lithospheric thickness. And however, because ocean depth seems to flatten at about 70 million year old, we often use a modification called a plate model. So in plate model, we have the flattened oceanic depth. So instead of getting inclined after 70 million year old, it gets flattened. So we are going to assume this also in the plate model, that is a modified version of half space model. So it assumes that the lithosphere evolves towards a finite plate thickness L with a fixed basal temperature Tm. So in this model, the temperature vary as a position and depth, and is given as T x comma z is equal to Tm in bracket z by L plus summation n is equal to 1 to infinity Cn exponential minus beta n x by L sine n pi z by L. So where Cn is 2 pi by n pi, beta is r square plus n square pi square to the power under root minus r, and r is equal to Vl by 2 kappa. The constant R, known as thermal Reynolds number, relates the rates at which heat is transported horizontally by plate motion and conducted vertically. Evolution of the oceanic lithosphere. So now we can view the ocean depth within the evolution of oceanic lithosphere, heat flow, and several other properties of the oceanic lithosphere as observable measures of the temperature in cooling lithosphere. Because the observables depend on different combination of parameters, they can be used together to constrain individual parameters. So these are the observables: young ocean depth, old ocean heat flow, geoid slope. So basically, geoid is a function of the gravity field that depends on the weighted integral of the density, and it also varies with age. So the depth depends upon the integral of the temperature, whereas the heat flow depends on its derivative at the sea floor. So you can see the young ocean depth is proportional to the temperature and has an integral over the depth, and that reflects k under root alpha Tm. Alpha is the coefficient of thermal expansion here. For old oceanic depth, this is integral of the temperature with respect to depth, and it is having alpha Tml. And old ocean heat flow is basically k Tm by L, that reflects. And similarly, the slope of the geoid, that is a function of the gravity field, depend on the weighted integral of the density, that also varies with age, and that has expressions something like this. So what is the summary of today's lecture? It goes like this: the temperature as a function of depth and time is given by one-dimensional heat flow equation, that is delta T z comma T by delta T is equal to K by rho Cp delta square T z comma T by del z square, that is further equal to kappa del square T z comma T by del z square, and the solution can be given from this particular expression, where error function can be represented as something like this: the temperature at a depth z for material of Ht is represented by this expression. If you consider the sea floor temperature Ts is equal to 0 degree centigrade, then it becomes something like this. So you can see the temperature at depth z for Ht is proportional to error function z by 2 under root kappa T. So then we discussed about the isotherm, which is having the constant argument of the error function. So Zc by 2 under root kt is equal to C. So Zc is equal to 2C under root kappa T. The temperature and thus density in the cooling lithosphere vary such that at point Z, T, the temperature is T Z, T and the corresponding density is rho Z, T is equal to rho m plus del rho by del T. T Z, T minus Tm is equal to rho m plus rho dash Z, T. Density perturbation for the half space cooling model is rho dash Z, T is equal to alpha rho m Tm minus T Z, T is equal to alpha rho m Tm 1 minus error function Z by 2 under root kappa T. The isostatic condition for ocean depth will give you this expression where you can see the depth of the ocean is represented by ht 1 by rho m minus rho w integral ht to mt rho dash Z, T del dz. And in this you have seen the ocean depth basically increases as a square root of the plate age. So basically when you will solve this, then it will be 2 under root kappa T by pi alpha rho m Tm by rho m minus rho w. For plate model, the temperature vary as a position and depth, which is given by this expression. These are the references of today's lecture. Thank you very much. Bye bye.